Let's now take a look at one more ice table problem. So in this problem, we're asked to consider the following reaction for the decomposition of N2O4 gas into 2NO2 gas. And we're told the value of Kp for this reaction is 64. We're told that a certain initial pressure of NO2 is placed into an otherwise empty container, meaning that there is no N2O4 initially. We're told that at equilibrium, 35% of the initial amount of NO2 remains, and we're asked to determine what the initial pressure of the NO2 was. So this is another problem where we have to kind of work backwards through the problem. So often we have questions where we're given the exact value of the initial pressure or concentration, and we have to figure out what it is at equilibrium. In this problem, we're told stuff about equilibrium, and we have to work backwards and find what we initially had. But again, the method for setting up this problem is going to be very similar to what we've seen in previous problems. We're going to start by writing out the reaction and setting up an ice table, because that's how we're going to be able to connect the initial and equilibrium states to one another. And we'll write the Kp expression out, because that kind of helps us remain focused on what information we're looking for and what information we're being given here. So I have a lot of practice already with writing ice tables, and a lot of practice with writing K expressions. So I'm going to just write it all out, and it's going to be ready for us in the next slide. All right, so now we have the ice table set up, and we've written out the Kp expression. The next thing for us to do is to begin filling in the ice table with the information that we know. So this problem tells us that there's some initial amount of NO2, but we're not told exactly how much it is. So when we fill in the initial line for the NO2, since we don't know what it is, we're just going to define some variable. And you can pick any letter that you want for this variable except for x. Like, don't use x because we've already allocated x for being used in the change line. So pick any letter you want. I'm going to pick A for the NO2. And we're told that the container is otherwise empty, and so that means that there is no N2O4 initially. 0 there. Now we can work on filling out the change line. So for this reaction, because there's initially no N2O4 present, we have to make some. And so what that means is that the reaction has to proceed to the left towards making at least some amount of N2O4. So we're going to increase the amount of N2O4 and decrease the amount of NO2 as we move away from that. Then we will say that for the N2O4, the change has to be plus x, because the stoichiometric coefficient there is 1. And for the NO2, the change is going to be minus 2x, because the coefficient for NO2 is 2. Then what we can do is combine the initial and the change lines to get the equilibrium line. So x for the N2O4 and A minus 2x for the NO2. All right, what we can do now is take the values that we have on the equilibrium line, and we can plug them into the Kp expression. And when we go about doing that, we're going to pretty quickly find out that we're going to get stuck here. But let's write it out anyway. We're going to have 64 equals, for the NO2, that's A minus 2x, and that's squared, over for the N2O4, that is just x. Now, the reason why we end up getting stuck here is because in this equation, we have two unknowns. And you can't just solve one equation with two unknowns in it. We're going to have to come up with a second equation that relates the two unknowns to one another, so that we generate a system of equations that can then be solved. So find some way to relate A and X. And the way that we can go about doing that is by looking for unused information. A piece of unused information that we have is, we were told at equilibrium that the pressure of NO2 is 35% of the initial. So let's take that sentence and turn it into the form of an equation. So what you can say is that at equilibrium, PNO2 is equal to 35%, expressed as a decimal, is 0.35, of means times the initial. Now, we had defined in this problem that the initial pressure of NO2 was A, so we can say that the pressure of NO2 at equilibrium is equal to 0.35 times A. Having said that, we can take this expression, PNO2 at equilibrium is 0.35 times A, and we can incorporate that information into what we have in the ice table, right? We could just put it here and say that A minus 2x is the same thing as 0.35A. Therefore, what we can come up with is our equation. So when we set equal to what the ICE table tells us, a minus 2x, what you get is 0.35a equals a minus 2x. This now allows us to generate a second equation, which will now allow us to solve the system of equations and unknowns. So our goal here is to find what the value of A is, right? The problem is asking us to find the initial pressure. And so if we want to find what A is, we need to get rid of X. We need to substitute X out of this equation. So what I'll do is I will solve this expression in the form X equals blah, 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 because when I do that, I'll be able to get X out. So to isolate and solve for X, what I'm going to do is first maybe add the 2x to both sides. So I get 2x on the left, and then I'm going to subtract the 0.35a from both sides. So I have an a that's already present on the right-hand side, and then subtract the 0.35a from both sides. So that moves it over there. What I then get is 2x is equal to 1 minus 0.35 is 0.65a. Now, to isolate x, divide both sides by 2 to find that x is 0.65a over 2. And so x equals 0.325a. Having determined that x is equal to 0.325a, we can now take this expression and use it to substitute x out from the KP expression. So we're going to plug it in right here. We're going to plug it in right there. So what we have here is that 64 is equal to the quantity a minus 2x. And, all right, so a minus 2 times, we said that x was 0.325a. Quantity squared over x, and again, x is 0.325a. Now we'll go about simplifying this expression and solving for a. So 64 is equal to the quantity a minus 2 times 0.325a is 0.65a. Quantity squared over 0.325a. So 64 is equal to 1 minus 0.65 is 0.35a, the quantity squared, over 0.325a. This is identical, what we have in the numerator, right, is identical to what we defined earlier in the problem, right, that at equilibrium, the pressure of the NO2 was 35% of the initial, or 0.35a. All right, now what we're going to do is apply that squared, and don't forget that this squared applies not just to the a, but it also applies to that coefficient of 0.35. So don't forget to apply it to both of those things. What we're going to get is 64 is equal to 0.35 squared is 0.1225, and then a is squared as well, over 0.325a. So what we have here is a factor of a squared on the top and a factor of a on the bottom. This factor of a on the bottom cancels out one of the two factors of a that you have on the top, and that simplifies things down a little bit and allows us to avoid a quadratic equation. 64 is equal to 0.1225a over 0.325. Now what you can do is evaluate this fraction, 0.1225 over 0.325 comes out to 0.376a. And lastly, divide the 0.376 on both sides. And what you find is that A comes out to be 170, and so the initial pressure of the NO2 was 170 atmospheres. And that gives us another example of solving an ICE table problem that requires the use of maybe some more advanced algebra and solving a system of equations and unknowns. But hopefully this video shows you, and also the other videos that you've seen, have shown you that even the most complicated problem can be broken down into manageable steps, and it could be reduced down to solving an algebra problem. So that brings us to the end of this section. In the next video, we'll begin section 6.8, which deals with Le Chatelier's principle.